Dr. M.A. Bhagaveni, Professor, Department of Electronics and Communication Engineering, College of Engineering Gindi, Anna University, Chennai. Dr. M.A. Bhagaveni graduated from Government College of Technology, Coimbatore, has completed her Masters and PhD at College of Engineering Gindi, Anna University. Her field of interest includes cognitive radio, ad-hoc networks, wireless sensor networks, and wireless communication. She has completed 2 projects, one for CVRDE and the other for DST. She is the recipient of Young Scientist Award from DST. She has got 2 Best Research Paper awards in international conferences. She has published more than 70 research papers in reputable journals and conferences. She is author of 2 books. The one is Analog and Digital Communication and the other is Cognitive Radio, an Enabler of Internet of Things.
Welcome to UGC lecture series on BSc Electronics Honors Practicals. This session we are going to see about demodulation. In this we will be covering the contents like amplitude demodulation, advantages and disadvantages of amplitude modulation. For experimentation purpose, we will not be taking up signals with many message signals or with many carrier frequencies. To see the signal properly and have simplicity in mathematical calculations, we just see a single tone modulation. In that case, m of t is nothing but a signal with only one frequency. When we take voice, I have already told the voice occupies between 0 to 3 kilohertz. A lot of frequencies are within 0 to 3 kilohertz. So, we cannot just appreciate the process of modulation or understand easily if you are going to write cumbersome equations. So, to avoid those things, we go in for single carrier modulation purpose. So, single carrier or single tone modulation is, we are going to assume that m of t equal to a m cos 2 pi f m t, that is only one carrier, that is f m. C of t is nothing but the carrier signal, its amplitude is AC, cos 2 pi f c t is the carrier waveform. A m modulated signal will be AC into 1 plus the Ka here is written as Ka into m of t, right. Ka into am is written as mu here, then cos by 2 pi f m t into cos of 2 pi f c t. This is your am modulated waveform. The dimensionless factor mu, it is called as the modulation factor or modulation index or percentage of modulation. We need to understand this mu should be always less than 1. That is one of the constraints we have already seen. If mu is greater than 1, we get over modulation. So, we need to maintain mu, the modulation index, to be less than 1. Experimentation level, AM modulated waveform you can see as like this, a carrier signal whose amplitude is going to change with respect to the amplitude of the message. Okay. So, from this you need to pick up what is A max, what is A min. After taking up the readings of A max is between from here to here, A min is between overall where is the minimum most point you need to see, pick up A min, A max divided by A min, which is nothing but AC plus 1 plus mu divided by AC into 1 minus mu, or from this expression A max is nothing but AC into 1 plus mu, that is A max. A min is AC into 1 minus mu. If you resolve, you get mu to be equal to A max minus A min divided by A max plus A min. For example, you can assume you have a carrier signal, you have the amplitude of the carrier to be equal to some 6 volts. And your sensitivity with, that is Ka into Am, that is the amplitude of your message signal, the sensitivity of the modulator into the amplitude of the signal to be equal to 1, right. It is a modulation index. If I say 1, it means it is a full modulation. We have to assume a value less than 1. So, we will assume it is about 0.5. We will assume the value is about 0.5, mu equal to 0.5. What you will get as A max? A max will be equal to 6 into 1 plus 0.5. You need to verify that whether you are getting 6 into 1.5. Is it okay? that is 9 volts. A min equal to 6 into 1 minus 0.5. So, you should have got a value of 3 volts, okay, that will be A min. So, while doing the experiment you can just verify and see what is your A max, what is your A min. A min equal to 6 into 1 minus 0.5, which will be of 3 volts. So, having A max and A min, you can compute what is modulation index, that is mu. You can know what is mu. With AC voltage you can compute what is A max A min. If you know A max A min, you can compute mu. This is the other way of doing the same thing. So, mu will be 6 A max 9 volts minus 3 volts divided by 9 plus 3. Finally, you will end up with 6 by 12, which is 0.5. So, we got it back. This is how you compute your mu value. Mu is nothing but modulation index or percentage of modulation. So, depending upon what percentage of modulation you have, and the amplitude of the carrier, amplitude of the message, we get modulation index. We see what is the power of the AM signals, how much power you are going to transmit while transmitting the AM signals. We already know S of t is given as equation AC cos 2 pi FCT plus half mu AC cos 2 pi FC plus FMT plus half mu AC cos 2 pi Fc minus Fm of t. So, this is the output of a multiplier. The Fourier transform of this S of t, we have already seen. The transform of the modulated signal will be AC by 2 del of F minus Fc plus del of F plus Fc, where del will be the impulse function. 1 by 4 mu AC del of F minus of Fc plus Fm, F plus Fc plus Fm. So, you can just see, you can see the power amplitudes. What are the amplitude of the signal is nothing but the power of the signal. You can see it is AC by 2, it is half mu AC, half mu AC. One is over lower sideband, the other is over upper sideband, and this is the carrier value. When you plot the signals, you will get like this. One is at Fc, Fc plus Fm, Fc minus Fm. This is for the lower side, negative part of the frequency. This will be your carrier, this will be your upper sideband, this will be your lower sideband. Since it is a single tone, you had only one frequency. So, we have not drawn it as a triangle, right. If it is a band of frequency, you would have drawn it as a triangle. Since this is a single tone, we have just taken up only one frequency as Fm. So, the frequencies that are occurring at your output will be the carrier frequency, the upper sideband frequency, lower sideband frequency. The carrier power is half AC square, upper sideband frequency is 1 by 8 mu square AC square, lower sideband frequency is 1 by 8 mu square AC square. Same thing is repeated over this side. So, the ratio of the total sideband powers to the total power in the modulated wave will be mu square divided by 2 plus mu square. For 100% modulation, the total sideband power is only 1/3 of the total power. Take it as 100% modulation, that is 1. So, 1 square divided by 2 plus 1, which is nothing but 1 by 3. So, even if you are going to use 100% modulation, the amount of power in one sideband is only 1/3 of the total power. So, that is about the general characteristics or explanation or theory behind AM. We are going to see how we are going to generate AM signals. There are generally many different methods realized to generate AM waveforms. The three general methods are, one is by using multiplier circuits, that is what we have seen as a simple diagram in your one of your slides. Then there is another method called as non-linear circuits by using non-linear devices like diode, transistor, etc. We can also generate by using switching circuits. By this method we can realize an AM modulated output. So, for simplicity we are going to see just out of these three only one method, that is your nonlinear circuits, that is by using transistors. Any nonlinear device is like your diode or your transistor you can use for generation of AM modulated waveforms. The output of the nonlinear device can be expressed as a power series. Output y of t will be equal to A times the input x of t plus b times input square of the signal, c times the cube root of the signal, etc. When x of t is very small, that is less than 1, the highest powers can be neglected and we can go for an approximation of only first two terms. So, therefore, when the input is x of t is the sum of two signals, that is m of t plus c of t, we go only up to x square of t, that is m of b times m of t plus c of t the whole square. When you make the square m of t plus c of t the whole square, right, we will be getting m square of t a square plus 2 a b plus b square, right. So, these are all higher frequency terms we can neglect, you can keep only m of t into c of t, that is what we need, right. So, you get the product of m of t into c of t. We have here, this is an example nonlinear device, you have two nonlinear devices we have. We pass m of t to this nonlinear device, to one of the nonlinear device we are going to send sum of m of t and c of t, to another nonlinear device we are going to send difference of m of t and c of t. So, sum of m of t and c of t is taken as x 1 of t, c of t plus m of t. So, the nonlinear device will carrier plus message towards the input of the second nonlinear device, we are going to provide this carrier minus the message cos of omega c t minus m of t. The output signals we are going to name it as y 1 of t and y 2 of t, then we are going to sum it up to get z of t. This z of t will be passed on to a band pass filter which has just the required carrier frequency to get the modulated output. So, what is y 1 of t and what is y 2 of t? Y 1 of t is the square modulator, a times the input plus b times square of the input. So, a times the input is repeated as such, square is a square 2 a b plus b square. So, in that a m of t is undesired, b m square of t is also undesired. We have 2 m of t into cos omega c t, this is the desired signal and all these are undesired signals. So, to remove away all undesired signals, we are going to pass the signal into the filter. So, there is another output of the nonlinear device 2. Once again, we will be having minus a m of t plus b m square of t minus 2 b m cos omega c t, then a cos omega c t plus b by 2 plus b by 2 cos omega 2 c. In this also all these terms are undesired, only b m of t into cos omega c t is only the required term. So, the z of t, which is nothing but sum of these two signals y 1 of t minus y 2 of t, this all these undesired signals, most of the signals will get cancelled. Finally, we are going to get only 4 b m of t cos of omega c t. So, we are getting only 4 b m of t into cos of omega c t, where m of t is multiplied with cos of omega c t. This is the desired AM modulated waveform. So, mathematically we have seen how a nonlinear device can produce your AM modulated waveform. Now, we go in for the process of demodulation to reconstruct the signal back. You have modulated, you have transmitted the signal over the channel. Now, we are going to receive the signal by using a demodulator. The process of recovering the message signal from the modulating signal will be called as demodulation. The AM demodulation can be achieved using diode demodulators. You can demodulate the signal easily by using simple diodes itself. So, this is the circuit of the diode demodulator. The operation is nothing but we are going to provide our AM modulated signal as input. The diode, you can just see this is nothing but a rectifier circuit. The diode is going to charge, it is going to act like a rectifier. It is going to charge to the highest peak, right, and the charged value is stored in the capacitor. When the diode is in the off condition, it is going to discharge. The capacitor is going to discharge through this resistor. This resistor is nothing but the load RL. So, you get your AM modulated signal as peaks of your carrier signal, and the peaks are going to vary with respect to the message signal. So, when a peak comes, through the peak the diode will conduct, and the conducted charge will go and get stored in the capacitor, Once for the first carrier signal, it is going to decrease, then the diode will cut off. For this part of the signal, the diode will get reverse biased, and therefore, it will get cut off. So, during that time the charge in this will start to discharge through tau, right. Before the complete charge getting discharged, we are going to see another peak of the carrier signal. We will be seeing another peak of the carrier signal, and therefore, the diode will once again start conducting, and the capacitor, the charge in the capacitor will start increase. So, like this we are going to track the envelope of the AM modulated signal. Once the envelope of the AM modulated is being tracked, we are going to get back the message signal M of t. So, there is a simple, very simple receiver part for AM modulation. For this purpose only AM modulation is used for broadcasting purpose, right. The transmitter may be a bit with a heavy gain, all those things it will be available, but the receiver is very simple circuitry which can be within a very small pocket radio. So, the most important characteristics what you are going to look here is only the charging time constant through which the diode charges and the discharging time constant. These two things we need to keep into account. For that, the envelope of the message is being tracked. So, for this purpose, the charging time constant is nothing but the forward resistance of the diode and the source resistance of the signal. You are going to provide a signal, the input resistance of the source and the diode forward resistance will be nothing but the charging time constant, that into C will be the charging time constant, and the discharging time constant is nothing but the load RL into C. The C is going to discharge like this. So, RL into C is the discharging time constant. So, we need to see that the signal is not going to be discharged too fast, for it not going to track the envelope of the message. So, the frequency what you are going to provide your signal, 1 by frequency will be the time period of the signal. So, 1 by frequency should be very much less than the discharging time constant RL into C, and this RL into C should be very much less than the frequency of the message, 1 by frequency of the message. Then only this diode demodulator will function properly to track the amplitude changes of the input signal. Same thing is bit explained with this input signal being your AM modulated signal. The diode, whenever the diode forward bias, it just conducts, the capacitor stores the charges. Whenever the diode get reverse bias, the capacitor discharge its charge. So, therefore, it charges up to the peak, discharges, once again charges up to the peak, discharges, charges up to the peak, discharges, charges up to the peak, discharges. So, this is your rectified signal. So, the capacitor will, the value of the capacitor and the value of the resistor will try to track the envelope of the message signal. So, this is the theory behind demodulation of the diode. So, there are advantages and limitations of AM are nothing but it is very easy to generate. We can generate using only a simple nonlinear device like a transistor, etc. And demodulation is also very simple, where you are going to use only a diode. The disadvantage we have already seen, it is going to consume 2 times the bandwidth and there is wastage of power. These are the disadvantages. So, with respect to this, we have just discussed only one type of modulation called as AM modulator. So, how was the principle of operation of AM modulation, how we are going to provide carrier signal and message signal, how the nonlinear device is going to produce your output, what is the frequency response of the AM signal, that is nothing but Fourier transform of the AM. Once you take the Fourier transform of the AM signal, you will be getting upper sideband, lower sideband in the positive frequency band as well as in the negative frequency band. So, how the spectrum of the AM modulation will look like for single tone modulation, which can be easily done in the lab. For the lab purpose, we are just looking into how single tone modulation is done. In general, the signals are over a band of frequencies. So, this band of frequencies will occupy a band in the upper band in the lower. So, that is why it has been drawn as a triangle, that is what we have seen. After AM modulation, we just covered how to demodulate the AM signal. Demodulation is a very simple circuit with just a diode and a discharging capacitor and a resistor. So, with simple circuit, the AM signal can be demodulated, and certain care should be taken about the discharging time constants and the frequency of the carrier wave and the frequency of the message signal. And also we concluded that with the advantages and limitations of AM. With some questions of class today. Now, you can define what is AM. AM is amplitude modulation. The amplitude of the carrier is varied with respect to the amplitude of the message. Such modulation is called as amplitude modulation. Then what are the limitations of AM modulation? Like what are the disadvantages? Limitations means what are the disadvantages? In the sense it is complex, it consumes double the bandwidth and it consumes more amount of power. We have defined what is called as modulation index, that is mu. Experimentally, how can we calculate mu also we have seen. So, define modulation index. Modulation index will be A max minus A min divided by A max plus A min. You can also say modulation index mu to be equal to Ka into AM, where Ka is the sensitivity of the device and AM is the amplitude of the message signal. You can also try to draw the AM waveform, draw an AM waveform. So, you should be very careful when we ask to draw an AM waveform. Most of the people will just draw the envelope of it like this and simply shade inside. That is very wrong. You have to put a dotted lines for the message frequency both at the top and the bottom, and inside the dotted lines you should actually draw the carrier signal with the amplitudes limited with respect to the amplitude of the dots, and the carrier signal frequency should be uniform. Then only you get a full mark for the drawn AM waveform, otherwise it is a wrong concept. Just drawing the envelope and filling up with dashed lines, it is a wrong concept. So, try to draw AM waveform neatly and see. So, in summary, we have seen all these things and these are the questions. We will continue in your next session. Thank you.